Okay, we should be starting. So what we're going to do today is we're going to be talking about multi-level modeling, reparameterization, and model comparison. But before, since we're roughly at the middle of the course, we need to do a midway evaluation, keeping it very short, with the idea that we should have a list of concerns and/or suggestions, which we should take into account for the rest of the course, and that we will reevaluate at the end, because one of the key points in the final evaluation is whether the midway evaluation has been taken into account. So we did already some of that last week, but we want to spend about 15 minutes on doing that. And what a list of questions that could help us focus the discussion is: what could I do better? What could you do better? What are we doing well and we should do more of? And how should we further improve, for instance, the notes? Because that's one of the things that I improve every year and might get better. Last week, we had a couple of points on the feedback to the assignments that should be more even. Of course, we had slides on Brightspace in advance. And I think that tempo and stuff were going well at that point. But if you can take with your group about 4 minutes to sort of think of a few points that could be brought up in class. Should no. We should start bringing it to the whole class. So which kind of things could I do better that could already take effect in the second half of the course? Yes.
Yeah, so I think we talked a little bit about that there might be, at least, I don't know, I speak from myself, but there's a gap between the examples and then what we have to do in terms of complexity. So that there might be, like, once you have to, so you see a same model of some pretty simple model, and then you kind of have to do reinforcement learning, that, you know, reparameterization and or like some sort of transformation mix, stuff like that. And then I don't know, at least for my part, once, because it's both a new language that I have to understand, and then it's also having to kind of make that jump yourself in complexity might be a little difficult sometimes. But I don't know if there's a good way around it. I think the advanced, like the GitHub pages that you have are really nice, but maybe have some of the more complicated examples, just having maybe a comment or so about like why do we structure it like this, and so that you know, okay, this is actually something that's stand specific or something that you usually do, like you usually have your price here, or you usually set the target thing like that, and then you can sort of see what is common for doing a stand model and what is more specific to this exact model that you want to do.
Okay. Yes. Good. I think this is a good point. In my head, and that's a bad place to be, that would be taken care of by you are free to develop whatever model you feel comfortable with. So if you want the extra challenge, you can take the reinforcement learning. If you want not the extra challenge, then you take the Winsay shift, which is comparable to the memory model that we've done in class. But that's a fair point. One of the things that as I was just realizing when I was going through the slides is maybe I like the elegance of starting with just estimating the theta, but maybe instead of making a second example on memory, I could already move towards reinforcement learning in class. And then the exercise for those who want the extra challenge could be make it asymmetric. Right? So learning from feedback positive is one thing, learning from feedback negative is different. Right, yes.
I think just to like, it's similar to Claire's point, but so our group uses the course notes quite a lot.
Oh, sorry.
Our group uses the course notes quite a lot, and they're very, very helpful. But I think that sometimes we are a little bit challenged by some consistency issues, or like maybe that, for example, looking at the RL model that you implemented in your course notes, you don't do it with the target notation, but in class we were introduced to the target notation.
Yes.
And obviously it's also a nice skill to be able to reconceptualize things by yourself. But when you're learning something as new as STAN, then it becomes extra difficult to do that calculation in your head.
Yes. Great. Okay. So this actually bridges me to the next point, because I fully agree the notes should be better. And I don't always have the time to update them as I update the slides. So if you find things that don't work in the notes, drop me an email, do a GitHub pull request. Somebody made a GitHub pull request and fixed an error. I think it was Alex, but I'm not sure. So that helps me sort of refocus on the stuff that is not consistent in the notes. Because my teaching strategy for good and for bad is that if I just take the slides from the previous year and they come in class and they teach them, I'm dead. I have no enthusiasm to master. So I need to go through them and say, oh, these things can actually be done better. And that means that every year the slides change. But if I finish the slides at midnight the night before, I don't have the time to do the course notes. And then I'm already thinking about next class and I completely forget about fixing the course notes. So if you use the course note, if you don't, not your problem. But if you use the course notes and you note stuff that are not working optimally for you, even if you just say these part sucks because there's no target, then that gives me the motivation to actually go through things and fix it.
I think it doesn't only apply to like course notes, but like when we were live coding with you, we also didn't do the target notation.
Yeah.
So like all those kind of things are okay, or are more easier to handle in courses where we are programming in a language that we're more familiar with. But
yes,
then it can be a little bit harder when you are also learning to program.
Yeah. Fair enough. Yes. Cool. Any more things that you think I could do better? You can also put them in the anonymous Google Doc if that's okay. What could you do better? How should we sort of encourage each other, scaffold each other in doing better? Yes.
I think I should study more. Because there's just a lot of really good info during the lectures and the classes, so sometimes I prioritize that like over reading more thoroughly or practicing at home. But maybe I should also say in terms of what you could do better, Ricardo. I don't know, we were talking about, it was really, really nice that one time you did live coding.
Yes.
Just to see it in practice instead of on a slide.
Mm-hmm.
But we were also talking about, we don't know when the time for that would be, because we really enjoy the lectures as they are right now, and the classes spent talking about polio work.
Yeah.
So we weren't sure where to put it. It's just nice.
My plan is that next week, if in this week's class we're all at a good point, next week I will do the live coding of the multi-level reinforcement learning and model comparison during the class, because the model comparison is not going to be part of these assignments. So I can do the lecture, you learn it, we see it in the live coding, and then we apply it in the next exercise.
Nice.
Yes.
That's super nice.
when my kids will be out of the house, then I'll also have time to do extra live coding videos. But that's not going to happen for 10 years. Very common. They're not going to happen for 20 years. Who am I kidding? Yes. Okay. What are we doing well and should we do more of? Because sometimes when I look at what I should do better, right, then I risk cutting away stuff that I shouldn't cut away. What are things that I should absolutely know do not cut away? Yes.
Not thinking that you're gonna cut it away, but your recordings and also the questions.
Okay, yes.
Both because you can look things up like after.
Yes.
I also really like the recordings, but we also talked about that it's very nice. The setup with portfolios really work well. The fact that we have time to like in classes to do them and like ask you if we are have anything.
Yeah.
But also the fact that we, I think it's like the first time in my cockside career that I've had that I haven't stressed through an entire portfolio because we have like time. The weeks that you give us to do it is very nice because then we can spend the week working on it and then come to class, ask you, and work on it next week. And it's like we have time to actually learn a lot from it.
Yeah. That's the nice thing about teaching at the master level, right? Because I can trust you to actually work without the strict deadlines. Yes. So thank you for allowing me to do something that fits you. Yes.
I was gonna reiterate like the floating deadline, but I appreciate that you gauge like where we're at as a class. Because it does give us time and like less stress to be able to sit with things and like having deeper discussions about the logic behind it instead of just trying to get it through and get it done. I feel like it is complex and it's nice to be able to sit and really.
Yeah.
understand it more. At least that's what we've been doing in our.
Yeah, that's also my feeling that who cares if you learn 3 models or 4 as long as you learn how to model, right? 1 or 2 makes a difference. 2 or 3 still makes a difference. 3 or 4, 4 or 5 doesn't, right? Yeah. Yes.
I just wanted to add that because I do really like the class feels low stakes. Like we're still learning and we're still doing a lot of stuff, but I don't feel the same type of pressure as I like in other classes where it's like, oh my God, we've got to figure this out because then the next thing is coming. It feels like I can just play with it and really learn how everything works, and it's really fun, and it's made it easier to learn also.
But where am I gonna get my prestige if not from stressing you? Yes. Yeah. Okay. Simple. Good. I think we covered the notes. If you have other suggestions on the extra resources. Yes.
Well, maybe we just discussed a bit. So I had some trouble, or like I was struggling a bit in the beginning to understand like what part of this matching pennies game is it that we are trying to infer something about, because there was a lot of stuff going on. We had to both code. So by now I understand that we have like one main agent, which is the process, the data generating process we're interested in modeling. And then the other agent is sort of considered part of the environment. Basically someone they're playing against. But for a long time it was unclear to me, because you are very open in allowing us to do it any way we want, but that also made it a bit confusing to me. Like, are we modeling both of the agents? Are we using just one? Does it have to be a random agent? Is that, I think maybe I like it as an example, but maybe make it more clear that one is the process we're interested in and the other is the environment. And maybe fix it. I think it's not bad to fix it a bit more because that can also be a bit helpful. Too much openness is bad for creativity.
Yeah, we'll see today, I hope, that for certain model, fixing it is bad. Because as you remarked last week, if we implement the memory model against a fixed random bias agent, we cannot recover properly both the coefficient for memory and the potential bias. And in that case, then an appropriate assignment, like with golden star, whatever, would actually say, no, we need to change the agent so that it changes the underlying biases. Because only if the underlying bias of the opponent is varying, then the two parameters can be separated, right? But yes, so giving more clear guidelines. Sometimes I get really excited that I'm teaching the master students. I'm just, yes, you do whatever you want, and then we'll make it work, right? Yes, but that's a good point. Cool. More comments? Good. I'll make a list and then I'll bring it back when we do the final evaluation. But if I'm not following on things that are dear to your heart, let me know. If you go through the notes, if you go through the slides, and you find things that are not clear, things that you think should be done differently, questions that you have the usual channels to ask me. And that helps me. Good. Am I recording? Yes, I'm recording. Before we move on to the multi-level model, we went a bit quickly last week through parameter recovery, but we had just gone through prior sensitivity, which was the very same conceptual operation at an abstract level. So I'm going to go very quickly through what we've done. And if you have questions that are still harassing you in your nights, sleepless nights because of cognitive modeling, please bring them up, right? So when we do these sort of large scale simulations where we need to run a bunch of simulations and a bunch of models, smart way of doing that is to create a function. Because if we create a function, then we can parallelize it. Even if you have just a normal computer with 4 available cores, that means 4 times as quick. When you're running 1,000, 20,000, 100,000 simulation, that makes a big difference. So we generate the random choices for an agent with noise. In that case, we put them into a table. We create a data list for Stan because Stan wants a list. We fit the model. We extract the rows that we are interested in. In this case, it would be the theta posterior, the true bias, and the true noise. And then we spit out those estimates. We load our parallelization machine. We create a data set that has the different parameter values that we want to simulate. In this case, it's the simplest possible case. So it has a bunch of rates, underlying biases, and a bunch of noises, right? Noise levels. And then we fit it. In this case, it's to a PMAP function, parallelizing map, using the package that's called future or FIR. That makes things easier. We fit it the set of parameter values, the function, and then it runs it throughout the cores that are available. And then here, I simply extracted the data recovery data frames that came out of the parallelization. And I say, please plot the true bias, so the true value of the bias in the simulation against the estimated bias. Geom point, right? Every sample should be a dot. Transparent. Geom smooth give me an approximate indication of whether there is a linear relation between those things. Split it in panels by noise so we can see things. Remove the ugly gray in the background. Right. This is what we find. With zero noise, we get uncertainty, of course. This is real life. Simulated, but right. It's but we get a very neat. The blue is the smooth, the red would be the ideal fit. We can see that with noise, as noise sort of moves away from extreme bias values, the slope gets shallower. And then whether it's good enough or not, right? You can see there is still a slope, but whether it's good enough or not depends on what we're trying to do. Questions on this general idea of simulations and parameter recovery? Yes.
Just one. So You use this parallelization technique,
Yes.
but isn't the MCMC sample already accessed? Like when you set the how many chains, parallel chains, aren't you already accessing all your cores? Is it you?
It depends on how many cores you have available.
You could do the parallelization inside the parameter recovery loop, and maybe there's not so much to gain.
Okay, so yes, good. There's three places where we can parallelize, right? We have, let's say, 1,000 simulations. We can parallelize, simulate the data, fit the model to these specific simulation. And from 1,000, it can become 500 or 250 according to how many cores. There's the chains that we're running for a single model within a single simulation, where usually it's a good idea to have 2 chains, right? At least to see whether they are covering the same posterior space. If we've done our homework before running the simulation, right? So we did all the model quality checks in general. We might sacrifice running 2 chains in favor of running 1, so we can have 250 times the time that it takes to run a simulation instead of 500 times the time to run a simulation. There's a third place where we can parallelize, that is splitting the gradient calculation within the Markov chain process. Right. So as the Quinn mobile is checking around itself as to the posterior density around itself, we can split those calculations and send them to different cores. That's called threading. The gain for that is margin, meaning that if you split it on 2 cores, it might take 90% of the time. Right? If you split it on 3 cores, it might take 85% of the time. So that's not really a good gain compared to parallelizing the simulation. So there's different efficiencies of parallelizing at different places in the process. For these kind of things, once we know that the model is working, the most efficient is to parallelize at the level of the simulation. Yes.
But this is more for, like, the workflow is for optimizing the code, right? Because
Yes.
you could also just simulate some data and save that and then do, okay.
Yes.
This, I would say for us, if it seems a little bit like over engineering, but it only takes 5 minutes to run 100 simulations, right? So is it not mostly?
But, so imagine that you have, let's say, 100 simulations, right?
Yeah.
But you also don't know exactly how many trials you should use, right? Because with a different amount of trials, you might get a different amount of parameter recovery. That's going to say, let's say you have even 3 values, you get the 3. But you also know that your trials might only be appropriate for a specific set of parameter values that you tested with before. So you might also want to test 10 values for the mean of the theta, 10 values for the mean of the standard deviation. That means 300 times 100, 30,000. Yes. So it's very easy to blow it up. And also I have that on the slide in a second, that's where we should be a bit careful. Because it's really easy to get excited and run a million different things. Also, now we're running 1 SID for each parameter value, right? So for the bias of 0 and the noise of 0.3, we're running 1 simulation. How much can we trust that? Should we run it 10 times? 100 times? Right? Yes. That's where it's very useful to parallelize, right? And then if you can run it on uCloud and run it on 64 cores, then you can go a bit crazy, not too much. Yes. So while we were discussing last time the impact of noise, I reminded you of that here. Here is a key question that is, how do you quantify whether this is good enough? Right? I'm a big fan of eyeballing things, right? But that's not always satisfying. It's not always satisfying for the reviewers. Ideally, we would have a utility function what are the costs of making a certain decision, given that the true value is this. But we don't often have that as scientists. Even people working in companies don't always have very clear perspectives on the costs and benefits of different jobs. So are there some things that we can use to support our motivated reasoning that should never neglect the eyeballing and thinking? How would you go at measuring how good that plot is? Yes.
You mean like with a number?
Yes, for instance, or a distribution, given we're Bayesians now. Yes.
You could calculate the fraction of cases where the 95% credible interval of the estimation has the true value within it.
So these are single samples, right? This is one model, and this is the full 100% credibility or confidence interval.
Yeah.
So you might say, is it always capturing? That has one problem, right? If the confidence intervals or credibility, if the spread of the posterior, if we want to be technical, is very big, right? Let's say that it covers every time from 0 to 1. It's always going to be inside.
95.
Yeah. So if you yeah, exactly. But you could say 60, right? But if it's very spread, right, you might still get it's a perfect fit. So if you look at this plot, which kind of analysis from method 1 does it bring to mind? In the fogs of the deep past. Correlation, right? That's something that you see reported a lot in the appendices of computational psychiatry papers that try to motivate and validate their models. You can run a correlation between the mean estimated value and the true value, which gives you one value. Again, it completely forgets that there is a distribution. Right? In principle, you could run a correlation for every sample, right? Because each sample, each iteration of the model will have a value here, a value here, a value here, a value here. So you could look at the distribution of the correlation values across the correlation between every single sample and the outcome. Not the outcome, sorry, the true value. If you have many parameters, that can become very expensive. There's things called measurement errors model, which allow you to include a measure of the spread as part of the predictor or as part of the outcome. And so this is just to say there is no one solution, right? You might have that actually the exact correlation is not something that you care about, but you're working on individual differences. So the important thing to you is that if participant 1 has a higher whatever than participant 2, right? And that is sort of reconstruct. Then what you could do is an ordinal correlation, or if we want to use a quick and dirty test, that you can see people building really complex Bayesian models to fit, and then they run a Spearman rank correlation on the true values against the estimated values. So simply relaxing the idea that this should be linear and saying, if this participant is below this other participant, is it reconstructed to be below the other participant? So there's a bunch of different ways. There's one of your colleagues from last year, Jesper, who's actually in his master thesis trying to figure out, can we do better than these standard things? Maybe he'll have something by June. Okay, Missing, as I was saying, multiple simulations. We could actually include noise in the model, and we'll do that in the lecture on mixture models. We could test the sensitivity to different prior values, and that would explode things. Good. I'm actually gonna skip this because, well, maybe I should. I shouldn't. Okay, so the idea is that we now have used simulations to do a few different things, right? We use simulation to understand the implications of the mechanisms that we assumed agents had to solve the task, right? We simulated data. We use simulations to create data where we knew the true model and the true parameter values, so we could fit our models on these data and know whether they were hitting the truth. And that really tells us about the powers of simulation. We have this little universe where we can manipulate every little knob and see what happens. We can understand model implications. We can understand the impact of choosing our priors so that we don't need to keep on feeling that this is very subjective. Actually, we can show what happens when we do different choices. We can do parameter recovery, right? We can systematically vary the full range of parameter values and see, is our model able to reconstruct the truth all over the place? We can do what it's called power and precision analysis. Right? Do you remember power analysis? Do you all know what power analysis are? Well, this is something that we've done. Well, actually, sorry, I really want to get to the multi-level, but I shouldn't go too fast. So we can do internal validity, right? Finding the true values. However, estimating the true values, doing parameter recovery, as I mentioned very briefly, doesn't happen in a vacuum. Right? For instance, right, we might expect that according to the experimental setup, our ability to do parameter recovery will change. For instance, if we have one trial per participant, it's going to be really hard to figure out reinforcement learning parameters. If we have 1,000 trials, it might be relatively easy to reconstruct parameter values, even for fairly complex models. We have a lot of information. But getting participants, especially if they're from difficult populations, from children to patients, right? It might be too much. But even if it's your friends, you might end up your exam session without any friends. Sometimes, right, you might be running your model against a random bias agent, and it's really having a hard time recovering the parameters, like in the memory model. It might be because it's the experimental setup that it's not giving the necessary information to separate the different parameters. Because if the random bias is playing right 70% of the time, and your memory model is learning that, the fact that it's playing mostly right could be both the effect of a bias towards right, or the effect that it has learned that there is a systematicity in the environment. So the stimuli that you're presenting to the model are making it very difficult to reconstruct the true parameter. So we need to be able to manipulate the structures of the environment from the number of trials to the agent that's playing against you to, and that's the second part of today, the number of participants, because we can learn from other participants about these specific participants we're treating. And that's part, or is that's the superclass under which power and precision of operations, under which power and precision analysis come in. So power analysis, and I was having fun with the PowerPoint designer, has nothing to do with that kind of power, but yes, It's a tool for type 2 error control, which is very central in frequency statistics. It's less central in Bayesian statistics. But the basic idea is that if we were to repeat the experiment n times and the conditions were X, let's say a difference in underlying learning rate of 0.1, a tau of this much, these many trials playing against this specific agent, blah, and we set alpha, the needed p-value, to z, usually 0.05, we would correctly reject the null y% of the time. That's your power. Y is your power. The number of times that in a very long sequence of repeated experiments with the conditions that you're using would correctly reject the null, would correctly get a p-value below 0.05. All right, so we can set y to 80%, very standard. We simulate data varying the amount of simulated participants or simulated trials, and then we map when do we get 80%. So we might have 10 participants, 100 trials. We run 1,000 simulations with a difference between two conditions of learning rate of 0.1. We keep everything else fixed, the same tau of 5, whatever. And then we say out of 1,000 simulation with 10 participants, 100 trials, this is the amount of times that we get. We correctly reject the null hypothesis. We get an estimated difference in the right direction and a p-value below 0.5. Now we increase the number of participants, 12, 14, 16, 17, 20, blah, blah, blah. And we see how the number of times that we correctly reject the null hypothesis changes. We do the same with the number of trials. And then if by default, right, our participant can only take 10 trials, and we only have money for 50 participants, we can say, what's the power of that? If we actually can plan things a bit more reasonably, we can say, well, right, we can see here that increasing the number of participants would cost us 100 krona per participant. And that's something we can afford. So we're gonna keep the number of trials as low as possible and increase the number of participants. If it's a rare population, what we might want to do is to say, well, actually, we cannot really get more than 10 Moebius patients in Denmark. That's a rare condition where your face is completely paralyzed. We had a case, we got everybody in our age range in Denmark and it was fine. Then we need to figure out how many trials. This is how a power analysis functions, right? When you're using it planning. It doesn't make a lot of sense in Bayesian statistics because we don't have a p-value. We could approximate it, as you were saying, we could take the posterior and we could say, when is 95% of the posterior correctly excluding 0? But it feels kind of hacky, right? We went all the way, all the trouble to become Bayesian, and then we're still using p-values. So what Bayesians would do is to say, actually, we don't really care about rejecting null hypothesis. So as Bayesians, what we care is to have a good enough posterior. What is a good enough posterior? Is a posterior that allows us to say something meaningful and is not spread out throughout the whole parameter space. That is, the more precise the posterior is, the better. The more informative our inferences become. If you remember, when we have those plots where we plot the prior and then the posterior, the more peaked the posterior is, the more confident it has become, the more it has learned from the data. Right? And we want our models, our posteriors, to learn from the data. Otherwise, we didn't need the data, right? So another way of thinking about this problem is, for instance, let's say that we observe in our simulations that a difference in learning rate of at least 0.1 will make a big difference in behavior. Right? Which means it's a good target to be able to identify. If we want to identify a difference of 0.1, right, we want that our estimates of the learning rate in the two conditions or in the two populations or whatever our contrast is, right, is half of that. Because that will minimize the probability of overlapping if there is a difference of at least 0.1. Does that make sense? So what we can say is we can say we want the precision of our estimate to be no more than 0.05. Again, we're making a decision, but it's not about rejecting or accepting an hypothesis. It's about having estimates that are below a certain uncertainty. It still irks a bit to make a dichotomous decision, but it's the alternative way of planning your analysis. Does this make sense? Do I do a lot of precision analysis? Not really. I do a lot of parameter recovery. Even when I'm assessing a contrast, right? I say, what if the contrast is these, and then these, and then these, and then this, right? How does the plot look like in this range of conditions? How does the plot look like in this range of conditions? I tend to do that sort of things. But it's nice to have the tools to do something more dichotomous if your boss requires you to do that. Or if you want to have a safety rule. Good. Now we're going to take a 10 minutes break, and then we're going to get into multi-level modeling. Okay, we're getting to the exciting part. Multi-level modeling. You all remember everything about multi-level modeling, right?
We do.
Okay, so the idea is that so far we've been estimated one agent at a time, but agents are not islands, right? Oh, sorry. Yes. Right, agents are expressions of a population. In many cases, especially in lots of scientific research, we might actually not care about the individuals. We might care about people in general who undergo these specific condition. Drink coffee before cognitive modeling, drink chamomile before cognitive modeling. What's the difference in that manipulation so that we have a general estimation that could apply in principle to an average of infinite or of indefinite samples, right? But in many cases, we actually care about the individuals. If we are working with any kind of patient population, right, we might want to know how the effects are related to symptoms. We might want to know how many people are actually affected by the condition, and not just what the average effect of the condition is, right? I often, right, worry that if I get an effect of whatever, let's say 0.2, right, this might be because there's Peter and I don't know, Maria and Joseph that have this big effect, and everybody else is flat, right? Yes. Or we might have a well-behaved effect where everybody is showing exactly the same effects. These are important things to know, even in our experiments. So the parameters that we're trying to estimate, the difference that coffee versus chamomile does, the difference that positive versus negative feedback has, right? Have hierarchical structures, meaning that there is an average learning rate of everybody who's in that condition, and there is an individual learning rate for each participant. And we want to estimate both. Or, right, we might have that in a meta-analysis, we have an effect that is estimated within each study. We might have an effect that's the average across the studies run by the same lab who use a specific machine, so has a specific incentive to get positive results. And we have the average expected effect across all the studies of that phenomenon. Right? Or we might have that if we subject participants to different stimuli, right? We have the average effect of stimulus 1, the average effect of stimulus 2, and across all the stimuli, an average effect of the condition. Right? So these are the kind of things that we're trying to describe when we do multi-level modeling. Right? What if there are multiple levels at which we're estimating the parameter? So if we take our stupid, silly example that you will not be able to generalize to your complex assignment, we have a choice, a set of choices in the matching pennies game, which is generated according to a Bernoulli from an underlying theta, a parameter, a tendency to pick right. We have, of course, well, we can represent that there's multiple trials. This is the Plateman notation. We put like a quadrangle around it, and we put a subscript T for trials. But B's is going to be repeated by I subjects. If we just do this, what we're saying is that each participant in each trial is going to have a choice, but the underlying parameter that is generating these choices is invariant, is exactly the same across all the participants. Right? Which is kind of a stupid assumption, actually surprisingly common, especially in older articles. And it's what is called full pooling. You're assuming that all the participants are part of the same thing without stratification. And so you can use all the data of all the participants of all the trials to estimate this one parameter. Wouldn't life be easy if things were like that? That's the theta parameter. If we want to indicate that that's not the case, right? What we can do is we can say, well, actually, no, you silly goose. Right? Theta is changing by participant. So theta as a subscript I. Yes, I
don't know if this is relevant, but was the assumption made because if you set up your experiment such that you believe that you're really truly sampling randomly from the population, your participant pool, then it shouldn't matter as much.
But the point is that there is variability between participants.
There is.
Yes.
But if they all have, like you said, hierarchically speaking, if the average holds, then it might still be true, even though you're missing that specificity of the individual.
You're ignoring the noise. You're ignoring a source of heterogeneity that makes your estimate more confident than it should be. So the reason it was done was it was easier statistically, number one. Second, it gives you more precise results at the cost of error, right? Sometimes you had complex models, and before MCMC, it was really hard to get them to work. So I would say, well, if we put all the data together, it actually works. This model, what it's saying is that each participant is separate, right? Each participant has its own parameter. There is no hierarchy. They're all flat, right? One on the side of the other. This is the opposite extreme of this one, and it's called a no pooling model. It's what is still the most prevalent way of modeling cognitive models in computational psychiatry and in a bunch of other fields where multi-level modeling is tricky, and they haven't fully embraced the inner Bayesian that we should all become. Right? There is two reasons for doing this. It's simpler, right? Your model is going to take less time to run, and it's going to probably run into fewer issues of fitting. Second, there is a big worry in the field that we shouldn't pool together participants that are heterogeneous from each other. For instance, there is a really neat paper that says, well, people are proposing these multi-level thing, but if we put together participants with Parkinson's and their matched control, we have the fixed effect of the condition, meaning we estimate that there is a difference, but we assume that they all come from the same underlying distribution plus this difference. What happens is, as we will see, that the participants who are more diverse from the other, or more numerous, or more heterogeneous from each other, they get pulled towards the participants who are more homogeneous. And that decreases the difference that patients could have from the typical population, because as one of the big Russians, which I forget every year, said, like every happy family is happy in the same way, every unhappy family is unhappy in a unique way. Right? You can break things in many different ways. Atypicalities can go in more directions than typicality can. That's something that we see constantly in patients' populations. On average, patient populations are much more heterogeneous than the control population. So what's missing in between full pooling and no pooling? Yes.
We're estimating a group level theta.
Exactly, a partial pooling. Right? We say that instead of each theta being independent from each other and having its own prior, we say that each theta is sampled from a distribution that has a common mean and a common standard deviation. And these common mean and common standard deviation are estimated at the same time as we're estimating theta I. And given that we're Bayesians, right, theta mean and theta standard deviation have a prior. Does this make sense? Good. And then we can represent them there, and I can take out these thingy. Yes. Again, designer is kind of fun to play with late at night. We have full pooling where there is one theta, no pooling where there is a separate theta per each participant, and we have partial pooling, which is separate theta per participants, but they have a shared hyperparameter, or actually shared hyperparameters. So what if we have more than one parameters? Right now it was the silly example. Let's take the memory model, right? What we have here is things happen in a bunch of trials. Each participant goes through that bunch of trials. Those are the two platelets. What we observe are the choice of the agent I at time t or at trial t, the choice of the other agent I at time t, which determines an internal state of memory, right? Which determines theta together with a beta and a bias. Basically, that theta is, as we've seen, determined by bias I for that participant plus beta I for that participant times memory. Meaning that that participant might have a certain tendency to pick right and a certain tendency to follow the previous pattern in the other. And here we have the old equation to figure out memory, right? Does this make sense? Now, since unfortunately I keep reading papers, realize that if you want to be very DAG consistent and memory is a completely deterministic variable, you need to go and read that paper on how to represent it. I haven't updated my slides. It doesn't make a difference for these specific applications, just so you know. Bias I and beta I have a population level prior for the mean of the population and the standard deviation of the population. Right? Does that make sense? So we do the partial pool. We say they have shared variance. This is the win, stay, lose, shift, probabilistic win, stay, lose, shift model, which is very similar. But the idea is that we have, instead of memory, the choice and the other choice determine the feedback that we're getting at every round. And the feedback defines the theta together with the bias. How much do we follow the stay rule when we win? And how much do we follow the shift rule when we lose? Kind of things. Theta is equal to bias at theta at the level of the single trial for the single individual is given by the bias of the individual plus the win beta of the individual times the win feedback plus the lose beta at the level of individual times the lose feedback. Yes.
What was beta on the other one in the middle?
It was, so if you played before me every time right, I might be deterministically following what you're doing, or I might do that only 80% of the time. Right? I might not be completely determined by what you've been playing before.
Okay.
Because I might be exploring. So it's a probability of following the rule of memory, if you want.
But it also has a bias for being sort of random.
The bias would be if I'm right-handed, I might be slightly more likely to pick right no matter what you're doing. Right? This is just to make two different parameters, right? So we see that a lot in ape experiments, that chimpanzees who are right-handed will tend to pick much more right than what the condition would seem to dictate. And chimpanzees who are left-handed, they tend to be really keen in picking the left hand. So you need to really up the attractor on the other side to make them pick right. And so you need to model these biases, otherwise you get a very skewed estimation of the condition. There's an example in McAreeth's book on the altruistic food choice, if you remember. But in any case, right. We could exclude the bias, and here we would still have two parameters, right? Yes.
At one point, you mentioned random effects.
Yes.
And then you said, then we would take the difference from the population.
Yes.
When would you use what?
So these is describing random effects. It's saying there is a population level estimate from which the individual estimate is sampled, which means it will not be exactly the population level, it will be slightly different. Whether we implement it as a specific value, so the bias for individual 1 is 0.6, or whether we implement it as a difference from the population. That is, the bias for individual 1 is bias of the population plus 0.1, whatever. That is something that we deal with when we figure out how to make STAN work. But mathematically, it's equivalent, right? If it's just a value, or if it's the population level value plus the difference from the population level value, mathematically it's the same.
It's because I'm wondering if we also need to set a prior for that difference.
The standard deviation of the population level estimate is the average error that you make if you pick one participant, one sample from that distribution, one participant from that population, and try to predict its value of bias in this case from the value of the population mean. That's the prior of the difference. The prior for the average error, for the average difference between the individual and the population. Does that make sense? Reinforcement learning. Choice. Other choice determines the feedback. Made an error, sorry. This should go here. The alpha should go into the value. The value is determined. Why didn't I? Where did I put it? Oh, here. Sorry. The value at one point in time plus alpha determine the next value. And the feedback. Right. Given the value, we determine a theta, which is shaped by tau as well. And the alpha should go there. Sorry, I'll fix it. This is just to give you an idea of how these things works. And the two parameters that are individual level and then population are tau and alpha. And again, because unfortunately I read new stuff, you can see here we have represented in directed cyclical graphs, cyclic cycles, not only value feedbacks into itself, but also you can go from choice to feedback to value to theta to choice, which makes it not acyclical, which doesn't matter for this example because we implement the full model in STAN. But if you wanted to apply d-separation calculus, that is the causal inference calculus on these DAG, you would have to represent time. So you would have value at times t and value at time t plus 1 as two separate nodes, choice at times t and choice at times t plus 1 as separate nodes, so that you avoid creating the cycles. I know that some of you are really interested in getting the true DAG notation, so I'm putting those notes. Good. Now we want to get coding, right? How do we turn these representation into the actual code? So here, to start with, I simulate a bunch of random agents with a specific bias and some noise. And I get some memory agents with some noise to play against them. Why do I put noise? Because data is always noisy, right? So how do we, I need to set these away. Right, basically we have a bunch of choices. Well, actually we have a Bernoulli distribution which generates a bunch of choices. The Bernoulli distribution is determined by the theta value. Right, and that theta value is different for the different participants. Right? And they all come from the same distribution. So we have 100 agents, 120 trials, a noise of 0.2, whatever, a rate mean, so a mean bias in the population of agents that on a log scale is 1.386, which is about 0.8, right? It's a very big bias. We're making it a bit easy for our models to see things. We have a standard deviation of the population level theta of 0.65 in log of scales, which is roughly a 0.1 in a probability scale. So we will expect to see most of the participants between 0.6 and 1. When we look at the memory agent parameters, again, we're defining the population level first, because then we'll sample the individuals from the population. The alpha, so the bias mean is 0, so there's no bias. But there is a standard deviation of 0.1, meaning that there's going to be a slight bias in choosing right or left. The beta, so how much it's following memory, we're going to put it at 1.5. So it's actually really keen in following memory. Otherwise, it's going to be hard to infer. And we put a standard deviation of 0.3. Why these values? The exact values are really not important. We're sort of setting up our simulation at this stage. Then we can loop through the n of agents, 1 to number of agents. And what we do is we can extract a rate for that agent from a normal distribution with a mean of rate m and a standard deviation of rate SD. We do the same for the bias in the memory agent, the same for the beta for memory in the memory agent. Here we create 3 vectors. One for the choice of the random agent, another is for the choice of the memory agent, and then we want to keep track of the memory, the cumulative memory of the agent. And then we go through the trials where the random agent doesn't care about the other, right? But if the trial is equal 1, the memory agent will pick at random. It has no memory to start with. If it's from the second trial onward, it will generate its choice according to its memory and bias and beta format. We have made the function before. And then we save the different choices of the random agent, of the memory agent, the memory of the memory agent, and the parameters of the population and of the individuals. So we have all the data. Does that make sense? Good. Then we make sure that everything worked, right? So we do plot the behavior of the agent. We plot the proportion of right-hand choices for the random agents. We plot the proportions of the right-hand choices for the memory agents. We can see that across the different agents, like each line is one different agent, this is the proportion of right and left over the course of the 120 trials. And the memory agent, right, it's perhaps a bit more noisy because it's estimating the bias in the other, but it's roughly in the right ballpark. This is just a sanity check, right? We develop these ways of understanding these agents. We want to see whether it's actually working. Then we want to see whether the memory agents are learning, right? Maybe I made an error in the function. So what I do is I say, if I take only 10 trials, I take the true bias in the other agent, and I take the propensity of the memory agents to pick right. We can see that as 10 trials, it's pretty widespread. There is a positive correlation. It's already picking it up because 0.8, it's pretty strong bias, but it's very broad. At 60 trials, it gets more skewed, or sorry, not more skewed, but more close to the diagonal. At 120 trials, even more. Right? It's showing that the agent is learning. would be really bad if it wasn't learning because we gave it infinite memory, right? And an underlying, an opponent that doesn't change its bias. Now we design the model. Right. Here we create the data, right? We subset so that we have the agent and the random choice. We add the number of trial. And then we transform our neat table or data frame, which is in a tidy format, that is, there is one row per observation so that the different agents are stacked one below the other. We now want a matrix where there's only the choices and there is I think it's, now I can never remember which direction it goes, but let's say rows are the trials and columns are the agents, right? Each column gives us the sequence of choices of one agent. Then we create the data, right? To Stan, we say, as before, what's the amount of trial that each agent goes through? What's the number of agents? And then we give the choices as a matrix. When we define the data block in Stan, it's parallelizing that one. We have an integer, that's the number of trials with a minimum trials of 1. Otherwise, what the heck are we doing here? There's an integer number of agents with a minimum amount of 1. And there is an array which has trials rows and agents columns, which is an integer, because again, it's choices, 0, 1, or 1 or 2, according to how we're coding it, which is age. So this is the big change so far. Instead of feeding it vectors, we're feeding it matrices. Yes, right? So remember that what we want to do, right, is now to define individual level parameters, which are constrained by a population level parameter. So parameters, we have a real theta mean. We have a real theta standard deviation, which has as a lower boundary 0, because a negative standard deviation doesn't make sense. And we have an array of agents, a vector, in this case, which is a real number, which is the theta. Does that make sense? It's the vector of these ones. And then we're trying to have those two values up there. Our model puts a prior on theta m, the mean for theta, the population level, and puts a prior on theta standard deviation. The prior is simple for the mean, right? It's normal with a mean of 0, standard deviation of 1, because then we're going to put it in a logit scale, and all is good. The standard deviation is slightly different because not only we're putting a normal with a mean of 0 and the standard deviation of 0.3, but we're also saying subtract from that the log, and now I need to, log complementary cumulative density function. What does it mean? It's simply the complementary function that will say that every number below 0 will have 0 probability. Yes.
Can I ask a potentially stupid question?
No question is stupid.
Okay, it's just the target syntax.
Yes.
Is it the same as saying theta m sampled from, for instance, in this case, like with a tilde?
Okay, yes. So the effects are the same.
Okay.
The reason for which we're using target is because we want to remember that at every iteration, the log posterior probability, that is the thing that we're trying to estimate, and the thing that is going to determine where we're going next, is determined at the same time by all the things that have target in front.
Okay.
So they get to be put together.
I see.
That's really the reason for the target notation.
Okay, but the effects are the same.
Yes.
It's just is like, yeah.
So basically what Stan is going to do is to convert your notation into the target notation.
Okay.
And since we're nerds, we like to make it technical and
Of
special,
course.
right? But it's the same.
Okay, great. Thanks.
Good. So this is basically saying transform this normal distribution into a truncated normal distribution. Then we say that theta, which is a vector, right? It's going to be 1 per agent, is sampled from theta m, theta st. So normal distribution with that mean and that standard deviation. Then we can loop through the agents and say that the vector of choices in the column I, all the choices of these agents, since the random agent doesn't care about time, doesn't care about history, right? We can take all of them at the same time, is generated from a Bernoulli distribution where the theta is on log odds. And here is the theta I. A different theta for each participant. Does that make sense? This is your first multi-level model. Yes. So what would be next, right, is that we have the generated quantities in which we want to support our model quality checks that we've discussed. So we would want to save the priors, so we don't need to generate them post hoc. We want to make prior and posterior predictions. And in principle, we might want to make prior and posterior predictions for the population. That is, were we to pick a new sample of participants, a new sample of agents, where would we expect their average to be? But we might also plot and save the posterior and prior predictions for the individual level, right? Which could be, if we were to pick a new participant that we haven't seen before, what should we expect from that participant? Or if we pick the specific participant, right? What are the predictions of the model for that specific participant? We do sample, comment, stand, diagnose, which is simply a way of getting some feedback on whether there were divergences and stuff. Here it says all transitions were satisfactory. There were no divergences. The potential energy was never broken. If you remember, right, when the Queen Mobile was going up the hill and suddenly it was in the middle of the air, right? The effective sample size was satisfactory. There were more than 200 effective samples all over the place. The chains are very overlapping, the one with each other. They're very hairy caterpillar. The processing was complete. There were no problems. This is very satisfactory. It never happens. We do the prior predictive checks, right? This is the kind of population level distribution of right choices out of 120 trials that we expect. This is the prior posterior updates for the mean rate, the variance of the rate, and the broader rate, that is the rate that takes into account both the mean and the variance. The posterior is very pointed in all the cases. The model has learned a lot from the data. I also plotted the true parameter value. Not perfect. We have been discounting, right, these area. So it's telling us, even with 100 participants, with these sort of priors, our estimates are going to be pulled towards 0.5 for the mean rate and 0 for the variance. We decide whether we can live with that or not, right? We look at the posterior of, I can't remember how many, let's say 10 individuals. This is the prior for them, and we can see for these different posteriors, they all seem to be in the same region, which is a good thing. They all seem to have learned. We can do the posterior predictive checks, right? We draw the expectations of right choices out of 120 trials after having seen the data for the population, not for the single agents. And we plot it also on top of the true empirical data, the single agents. You can see that the model has learned, right? And that roughly is in the range of the empirical data. It's really hard to compare the empirical data with the posterior predictions because in the histogram, we're counting how many times we have that value. And for the posterior predictions, we have as many values as the number of agents times the number of samples in the posterior space. So I generated a density function, which renormalizes, and this is how it looks. This is what also BRMS would spit out. I reproduced the same style. Does that make sense? This should be like refreshing what we've seen before. We do predictions for individuals, and we put their actual number of choices. And again, I should have probably made a line, but it seems roughly in the right ballpark. This is not parameter recovery yet. This is making sure that the model is not making any obvious error. We want to extend this to the memory model. This was the big plot, right? So we now subset from our simulation. Instead of random choice, we subset memory choice. We select memory choice. So we get the choices of the memory agents. The rest is the same, except that now we want also to have a matrix for the choices of the other person. Why? Because in that way, we can calculate the memory on a trial by trial basis that the model will use to estimate its theta. The data, right? Same as before, trials, agents, one matrix with the agent's choices, a second matrix with the opponent choices. The parameters, bias mean, bias standard deviation. This is the population level for the bias in the memory agent. The standard deviation again is a boundary at 0. Beta m, beta standard deviation. The standard deviation has a boundary at 0. And two vectors, two array, monodimensional arrays, one for bias, one for beta. Now we have, as before, when we were coding the memory stand model, a transform parameter where we pick the choices of the other, and on a trial by trial base, we update our memory of the estimated bias in the other. We create a matrix that has trial rows and agent columns, real values between 0, or I can remember between, yes, 0 and 1. Memory. We loop through agents. We loop through trials. If the trial is the first, then the memory is a check like it. 0.5, right? It has no idea which direction the bias is. If the trial is above 1 and less than the final number of trials, then the memory for the next trial for the current agent is given by the memory for the current trial for the current agent plus the choice of the other for the current trial for the current agent minus the memory for the current trial for the current agent. We're updating divided trial. We're updating the memory value. This is I use the formula of the Kalman filter. Basically, it gets updated less and less the more trial passes because you're more confident the more trials you've seen. It's just a way of doing the average without having to keep in mind the full vector of previous choices. Then some weird stuff can happen, right? The other chooses right the first two trials. Your memory is 1. We put it in log odds, as we will later. 1 becomes plus infinite, the model fails. The other is picked the first 2 times left, your memory is 0. We put 0 into log odds, as we will have to do. Becomes minus infinite, the memory fails. So here I put a brute force check that says if it's exactly 0 or exactly 1, push it a bit towards the center. Then we have the model. We have the prior for the population level, mean of the bias, population level, standard deviation of the bias, with the log complementary cumulative density function, which simply truncates it. The same for the beta mean and beta standard deviation. We sample each of the individual biases and betas from the population level. Then we loop through all the agents, and now the agents are reacting on a trial by trial basis, so we need to loop through all the trials. Where the choice for the current agent in the current trial is generated according to a Bernoulli distribution with a rate or theta in log odds, which is given by the bias of the agent plus the logit of memory, because we are in log odd space, right? We called it the model here. So that if the memory is above 0.5, it pushes things positively. It's a positive value. If the memory is below 0.5, it's a negative value, and log odds is going to push us towards minus infinite, towards left, times beta, right? How much we're swayed by memory. And generated quantities, I'm not going to go through the details of that, because what I want to close the class with today is, this is what happens, right? The model will start giving you lots of errors. Informational message, the current metropolis proposal is about to be rejected because of the following issues. Scale parameter is 0, but must be positive. Who knows, right? We let it run anyway. It takes a bit of a long time. And then it says, everything has finished successfully, but warning, 2 out of 2 chains have an estimate of their kinetic energy, which is less than 0.2. What does that mean? In itself, who knows? But basically what it means is that the model has found some funnels. What are funnels? Funnels mean that in some region of the posterior space, we can explore it optimally doing this kind of steps, right? Half a meter steps. But other regions of the posterior space are like in a pinball machine, right? They're getting narrower and narrower. So these kind of steps will just send us bouncing against the wall all the time. Or will make us cross the boundary, and we thought that we were in a region that had a high posterior density, and suddenly we look around us and there's nothing. which means that our Markov chain Monte Carlo sampler is not exploring the posterior space in a good way. Indeed, right, we do the diagnose and it tells us exactly the same thing. We look at the chains and we see that at the very least, the chain of the beta standard deviation is not a hairy caterpillar. The sampling of the posterior space is very autocorrelated, meaning that where I am at step 1 determines where I am at step 2. I'm not crossing it in any meaningful way.
Do you see the autocorrelation because it's such a smooth kind of line?
Yeah, because you can see that these are the iterations.
Right.
So you can see that it goes down, 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 up, up, right? So it's very easy to predict in which region it's going to be in the next one. If you take, that's also correlated, but the top right is less correlated.
Yeah. I just feel like if you had enough iterations, couldn't the plot just make it look like it was fine? Like because it's squeezed together.
Yeah, well, so you can see there also in the top right.
Yeah.
That it's correlated, right? It has these trends up and downs.
Yeah.
But we're also getting the warning from the energy.
Mm.
And when we look at the output, it's going to tell us that the R hat, so the measure of convergence is not going to be good.
Right.
Yes. And the effective samples is going to be low because each iteration is not going to give you new information. And let me see, this is, and also we can look at whether it has recovered the parameters and now it's crap. Yes. So next time we'll figure out what to do.